This is the relativistic slide rule. I think at 0.6 at the moment, and I've included an overview. That's my theory to do with the left-handed spin is unbalanced, so it collapses into beta decay, which is the weak force, when the right-handed spin is balanced, so there's no collapse, and that's the strong force. And then I've got a cartoon here where I've just showed the beta values of cosmological and microscopic particles and how they compare. And then I've put in Flavours and shown that you get the right partial charges on those anyons. So they're the anyons. That's where they are. And then there's the standard model. That's just a basic picture of the 3 pions. And I've also tried to put everything into the one picture to show how the right-handed spin is balanced and how it looks like colours are getting swapped. And I'll show it down here. So you've got a proton, and there's along this right-handed axis, it looks like the blue magenta is swapping places with the yellow-green gluons. So it just looks like they're just swapping places. And then it's likewise for the neutron right-handed spin. The strong force is the same, but it's instead of that positive pion being the axis, you've got this neutral pion, the green magenta one, being the axis. Then you've got the yellow-red gluon swapping places with the blue magenta gluon. So the same sort of thing, right-handed, both right-handed, and then and they're balanced. But then when you get this left-handed spin, you find that this left-handed one here, you find that the gluons are unbalanced, so it collapses. I imagine, this is my idea, that it collapses and you get beta decay. You get in this case the proton is heavy, would be heavy, and so it's going to decay, give off a positron and a neutron down the bottom, and that'll cause it to become a neutron instead. And likewise, if you've got a neutron and it wants to become a proton, then a left-handed spin is unbalanced again, and it will collapse onto that y-axis, and you get an electron given off and an anti-neutrino, and it will turn into a proton. Standard model at the moment. And then here just generally what happens, the same collapse, but it can be calculated on the complex plane as a measurement and its conjugate, being a conjugate pair, and can be calculated using either that formula or this one, which is the complex plane one. And I'll just put in the complex plane here. And this is like Penrose's idea that you've got your two lines of simultaneity due to special relativity, and so when a measurement's made, the conjugate travels backwards in time along the light cone into the past of the other light cone, and so that's how it can affect the probability of a successful measurement in the other experiment, which is in a different place. So time's going to the right, the left, because I've got it, my complex plane just happens to be on the y-axis. The real axis is the y one, so I've got 1 at the top, -1 at the bottom, 0 in the middle, and then I've got I on the left and -I on the right. That's just how I graphed it. And then they're the conjugate pairs, and it can be calculated, the probability of a successful measurement. And I've also done a bit of work on the diffraction grading. Seems like O is the object wave and R is the reference wave. It's like a strange coincidence. Here's my O and here's my R. So I'm just going with that at the moment. It's a pretty strange coincidence that I already had them down as O and R. And then you've got diffraction according to Bohmian mechanics. It's the same result, and the calculation. Here's the guy seeing the object in there. M equals 1. It's 1 wavelength